Well, hello and welcome to our first lecture, well, first real lecture of the semester for the Monday section of the class. And I'm going to, and this will basically be the same setup that we'll be using for the second lecture of the week all through the semester. Normally, I'll break the lecture up into smaller bits, usually say 3 segments of about 25 minutes each, and that way it'll equal about an hour and 15 minutes, the length of a normal lecture, but it'll be in smaller pieces, so it will, hopefully the video will play a little faster and won't take as long to load for each segment. So if you watch each of the segments in order, and I'll probably label them like A, B, and C, then you'll have the entire experience. Because of the logistics of doing a video and because I don't have access to the classrooms or anything, it's pretty much going to be me writing the notes on paper, which will kind of mimic what you would have seen if I were there in the room writing on the board. You'll get a better view this way, actually. You don't have to worry about as many reflections from the windows and stuff like that. But and unfortunately, you won't be able to ask questions directly. Although you do have the advantage of being able to back up and watch something again if there's something that's not too clear. I don't think that'll really be a problem immediately anyway, since we're starting with the first chapter, which is pretty simple, straightforward stuff. Let's see, homework problems for the first chapter. I haven't looked through all of them yet, but I will assign those very soon. And so those will be coming. I'll send you an email and I'll post them on D2L once I get those out. There, for this week, there will also be a second video, or second group of 3 videos basically, that you'll need to watch too, so that we'll get our 2 lectures per week in. And so you guys in the Monday class will have the pleasure of watching 2 videos in 1 week. Yay. Anyway, so to get to the start here with chapter 1, physics. Okay, so you might be wondering, what is physics? Well, it's a science that tries to understand the underpinnings of everything. And I underline that because I do mean literally anything. And by the way, if anybody has trouble reading my writing, either because the pen is not clear enough or just my handwriting is hard to read or anything like that, send me an email, let me know, and I'll see what I can do about it. Anyway, science or physics is the science that investigates the underpinnings of everything, literally everything. And that's everything from very small stuff and things like subatomic particles to very large, i.e. The entire universe. Because I believe I mentioned in class that in the world of science, really physics is the most fundamental of all the sciences. And really it's the broadest of all of the sciences too. Because if you investigate any area of science deeply enough, you'll eventually come to physics. You might have to go down pretty deeply to a pretty small level, but ultimately it's all about physics. And so subatomic particles, yeah, that's physics. Astronomy, the universe, yeah, that's physics. And everything in between. Physics is a little more scientifically. It's the study of the fundamental laws of nature. And when we hear nature, we tend to think biology. But actually, well, like I said, if you go down deep enough in biology, you get to physics. why do certain processes occur? Why do certain biomolecules react with each other? Ultimately, it's transfer of energy and stability, and that all comes down to physics. So it's a study of all the fundamental laws of nature that underlie all physical processes in the universe. And again, it's the fundamental basis of things like astronomy, obviously, engineering. When I say engineering, I don't just mean things like building bridges. I also mean things like electronics engineering. So design of cell phones and computers. Ultimately, that's all down to physics. Geology, transfer of heat within the earth, movement of substances through the earth's crust, things like that are all physics. And chemistry, again, things like the structure of the atom and why certain elements will react with each other in certain ways has to do with energy transfer. That's physics. Biology, geology. Wait a minute, did I? Yeah, I mentioned geology. Meteorology. Weather. Fundamentally, weather is due to laws of physics. And I'm going to put a big etc. because you can keep on going and going and going. Everything ultimately comes down to physics. The laws of physics can be applied to many situations. And those laws of physics, we'll get to this a little bit more when we do a bit on the scientific method a little later on, but scientific laws can often be expressed as mathematical equations. You have theories like the theory of evolution or the theory of relativity, which are large, sprawling collections of knowledge about various related situations that help us understand how things work on a large scale. Laws are usually very well proven and universally accepted, but they tend to be very focused and basically confined to like one area of science or one little phenomenon, like Newton's second law, force equals mass times acceleration. F equals ma, that's an equation. And it's very limited in its scope, but it's always, always true and universally accepted. The equations allow comparison of theory to reality. As does construction of models. And we'll discuss models a little more when we talk about the scientific method also. Models are sort of simplified situations representing a real life situation, or at least certain aspects of a real life situation. Oftentimes you'll construct a model so that certain aspects of it are accurate compared to the real life situation, but maybe not everything about it is accurate. So you'll focus on the parts that are accurate to help you gain an understanding of real life, but and then you'll kind of just ignore the parts that are not accurate. Like the models of the atom. Most of the models of the atom that we use in chemistry and sometimes in physics are not totally accurate, but they're accurate in terms of certain aspects that we want to emphasize at certain times. And that comparison of theory to reality can result in either a confirmation of the theory or refinement of the theory. So essentially, a theory is devised as sort of the culmination of a series of experiments where you take the results of those experiments and you sort of stitch them together into an idea of how a certain situation actually works. And then you can conduct more experiments. You can make your results known to other people so that they can conduct experiments in trying to replicate your results. If they basically find out that your results are not entirely valid, or that there are certain situations in which they're not valid, then you can either change your theory, or you can at least specify that your theory is only accurate in these situations here, but not these situations over here. So that would be like a refinement of the theory. Of course, if other people's work and your own further work confirms your theory, then hey, you're good to go. Your theory remains for the time being anyway. And again, that is getting into the scientific method, and we'll go over that in a little more detail later. The first big section we need to get into, and actually these sections that I'm covering here are based on lecture notes from the old textbook that we used to use. As I mentioned Monday, since we changed this at the last minute, I'm going to use the old notes for the first chapter, which covers the same stuff that the first chapter in our book covers. It's just the order varies slightly from place to place. So the next section in the old book was measurement and units. And our current new book covers that too, and actually I think that is the second topic it covers. So we're probably in sync, but anyway, it's all the same stuff ultimately. Measurement and units. Measurements are very important in science because you need to know the magnitudes of things. You need to know the sizes of things. And basically, measurement is how we do that. Measurement is when you basically compare the size or quantity of something to some reference. Oops. Okay, reference. Okay, so a measurement is a comparison of the magnitude of something to some agreed upon reference. So for instance, when you take a ruler and you measure the length of a pencil, say, you're comparing the magnitude of the length of that pencil to the agreed upon unit that's on the ruler. It might be inches or it might be centimeters. Either way, the unit on the ruler is the reference. Okay. And the units are the reference. And certain quantities, certain units are used for measuring certain quantities. So you have certain units that are used for measuring length or distance, certain other units that are used for measuring volumes, certain other units that are used for measuring weights, and certain other units that are used for measuring time, and things like that. Okay, the units. So the units can give you a hint as to what type of measurement you're making. If something is measured in inches, then you know right away that it's something to do with length or distance. If something is measured in in inches, it's definitely not a measurement of time, for instance. Something is measured in minutes, it's definitely not a measurement of weight. So we just from the units, we can know what type of measurement it is. And you can usually get an idea of the magnitude of the measurement also, since in practice, we generally try to choose a unit for a measurement that gives us a reasonable number. Okay, so for example, each measurement will normally consist of a unit, which is the reference, and a number. That is how many units are equivalent to the quantity you're measuring. So usually you want to choose a unit that will give you a reasonable number. Just for instance, if you're measuring the length of a pencil, you're probably going to be doing it in inches rather than yards. Because if you do it in yards, you're going to end up with a really, really small number. Or in even more extreme examples, the distance to Rochester is about 60 miles. Miles would be a measurement of distance, but inches are also a measurement of distance. You could measure that distance in inches if you really want to. It would be 3,801,600 inches. But you probably wouldn't do it that way because 3,801,600 is really kind of a pain in the butt number to deal with, whereas 60 is nice and convenient. So you'd probably choose these units. Whenever you see that a distance is being measured in miles, then you know right away that it's probably a fairly large distance. Whereas if it's measured in inches, it's probably going to be a fairly small distance, like the length of a pencil. On the other hand, the length of a standard sheet of trigger paper, like the one I'm writing on now, is 11 inches. 8.5 by 11. 8.5 inches wide, 11 inches long. That would be 0.000174 miles. Now, in this case, it's a small distance, so it would make perfect sense to use inches to measure it rather than miles, because you get a really, really small number if you're going to measure that in miles. Okay, for consistency, we tend to use what are known as standard units. So first of all, to narrow it down a little bit, generally in science, you use the metric system for measurements. The metric system would be basically what they use in the rest of the world, everywhere except the United States. Basically, I think we're pretty much alone now. Even Great Britain has started converting over to the metric system. So metric system would be things like centimeters, meters, liters, that kind of thing. Whereas the English system that we use here in this country would be things like inches, feet, gallons, ounces, things like that. So the metric system is used in science. But even within the metric system, there is a subset of the metric system known as the SI system, which stands for Système International. It's in French where they put the adjective after the noun usually, so it's SI. Also known as the MKS system. And that's the system that's used in chemistry and physics. It's a particular subset of the metric system. That is, it's the metric system, but there are certain units within the metric system that are officially used for certain types of measurement. And there are other units in the metric system that can be used for those measurements, but not officially, quote unquote. And so the official SI units are, well, as indicated by the initials MKS, for the quantity of length or distance, the unit would be the meter. That is the official SI or MKS, in fact, that's what M stands for, unit for distance or length would be the meter. Now, you can measure lengths or distances in science using centimeters or millimeters or kilometers, but what we mean by the SI system, those units were chosen for these quantities so that when you use these types of measurements in certain equations, if they're in the official SI units, then you will get the desired SI unit out of the equation as the answer. And there are some equations later on, like when you're doing calculations involving energies, say, or electrical power or things like that, where you want the answer to come out in certain units. And if you use, say, centimeters instead of meters, then you're not going to get that unit out as the answer, not the unit you want. But if you use meters for any measurements of length, then you will get the units out that you want as the final answer. So that's why we sort of designate this as the official unit for length. You can measure things, like I said, you can measure lengths in millimeters if you want, but if you are going to use that length in an equation, you're probably going to have to switch it to meters before putting it in the equation. So there's length. There's also mass. And mass is just a measurement of the amount of matter in an object. It's related to weight, but it's not the same thing. And we'll get to the distinction in a little while. The official SI unit for mass is kilogram, the symbol for kilogram being kg. And a kilogram is 2.2 pounds. I forgot to mention that a meter is 39.37 inches. Or about 1.1 yards. So a meter is about a yard. A kilogram is about 2 pounds, ballpark figure. And as with meters for length, you can measure masses in units other than kilograms. If it's a very small mass, then you might want to use milligrams, which are very small units of mass. But again, if you're going to use it in an equation, you're probably going to have to change it to kilograms first before putting it in the equation. And then the third basic quantity that you would have to measure would be time. Time is measured in seconds. And actually, this is one case where the metric unit is actually the same as the English unit. So 1 second in the metric system is the same as 1 second in the English system. It's 1/60th of an hour, and, 1/60th of a minute, and 1 minute is 1/60th of an hour, and 1 hour is 1/24th of a day, and so on and so on and so on. If you have a long time to measure, you can measure it in minutes and seconds. But again, if you're going to use it in an equation, you're probably going to have to change it to seconds if you want to get the right units out as an answer. So seconds would be the standard unit. These are the main fundamental quantities that you might have to measure. There are lots of other measurements, of course, that can be done, but most of those are actually what are known as derived units, which can be derived from some combination of length, mass, and time. So things like area, for example. Area is length units to the second power, length times width. Width is just another form of length. So length times width is just length units to the second power. And so in the metric system, we have derived units. Area, for one thing. Area is usually considered to be the area of a rectangular space, although, of course, many spaces are not rectangular, but it's treated that way anyway. And the area of a rectangular space would be length times width. Width would be used, you'd use the same units as you'd use for length. So essentially area is going to be length units squared or meters squared. So square meters would be the standard unit for area in the SI system. There are other units like acres and things like that, but ultimately if you use it in the equation, you're going to need square meters. For volume, again, the SI system treats volume as if it's the volume of a regularly shaped three-dimensional solid, which would be length times width times height. Which gives you, and length and width and height are all forms of length really, so you'd use meters for each of those measurements. So you'd have length units to the third power, or cubic meters. Of course, in the metric system, you also have liters and milliliters, which can be used for volumes. And they often are, particularly for volumes of liquids or gases. But ultimately, if you're going to use a volume in an equation, many times, not always, but many times, you would have to change it to cubic meters in order to use it there. Okay, I'm going to stop the first segment of the lecture right there, and I will start with segment B in just a moment.